Okay, so today we will be discussing first and second order constant coefficient differential equations. For starters, all of you have either taken or are in differential equations, so you may know other methods in solving these problems. These methods will work, but we are here to teach you a single uniform method that will make your life easier when solving these problems in the course. Prior to doing some problems, I'm just going to cover a couple of definitions so that we understand this topic better. So, why are we learning this? When integrating inductors, capacitors, and resistors, we will need to solve a differential equation, generally to retrieve some voltage or current depending on the problem, with respect to time. This tutorial shows you how to solve very basic first and second order equations with predefined initial conditions. When doing circuits, you will most likely have to find these initial conditions based on the given circuit and its state. Now to talk a little bit about these formulas. This is the general form of a first-order linear constant coefficient differential equation. As you see, this derivative is a first-order derivative, hence the title first order. Now, when speaking of the solution is composed of two parts, the homogeneous solution, which is usually referred to as the natural response, and the particular solution, which is usually referred to as the forced response. Now, in the tutorial, we'll show you how to solve for each of these parts to end up with your formal solution. Now, speaking in terms of the second order differential equations, as you can see here, here's a second order derivative, hence the name second order differential equation. And just like with the first order equations, you will be finding two parts, the homogeneous solution and the particular solution. Just as before, each is referred to as natural response and forced response respectively. Now we're going to go on to just solve a couple of problems with you guys so that you can see just how to do these problems in the general format.
So this is the first example for solving the first order linear differential equation. We are trying to solve this equation 2 dy dt plus 4yt equal negative 3, and the initial conditions given is y0 equal 5. And this is the same equation with different notation. The basic steps are still the same. The first step is find the homogeneous solution. We will set this equation equal to 0 to find this homogeneous solution. So here I set the original equation equal to 0, and then we will assume a solution, which is yt equal e to the st, and this is what we do every single time for solving the first order differential equation in this class. Then we will plug this particular solution, this solution into this equation. We will get 2s e to the st because this is the derivative, plus 4st equal to 0. And then we combine it and get e to the st times 2s plus 4 equals 0. And we will call this 2s plus 4 equals 0 a characteristic equation. So since our final goal is just the final solution for the differential equation, and then we use it to solve a circuit, the explanation of S is beyond the scope of this video, but all you need to know is that we use this tool to solve this differential equation. So US in the characteristic equation. And then this is the form of our homogeneous solution. YHT equal A e to the minus 2t. So A is an unknown constant that we will find later on. And e to the st, s is minus 2. Let's go on to the second step. We will assume that ypt is equal c. Since this is a constant, that's why we assume c is a constant, and then y prime pt is 0 since c is a constant. And we plug ypt into the original equation. We get 0 because the derivative plus 4c equal minus 3. And then we find c equal minus 3 over 4, And this is our particular solution, ypt equal minus 3 over 4. Then we combine the two solution to get the complete solution. Yt equal yht plus ypt equal ae to the minus 2t minus 3 over 4. Then the last step is to apply the initial condition to find a. So our initial condition is y0 equal 5, and we have a minus 3 over 4 equal 5 because e to the minus 2t when t is 0 is 1. That's why it's a times 1 is also 1. So that's why we have this equation. And then we found a to be 23 over 4. And combine everything together, we found the final solution, yt equal 23 over 4 e to the minus 2t minus 3 over 4. This is the second example for solving first order linear differential equation. This equation we're trying to solve is 3 dy dt plus 2y equal e to the minus t with the initial condition that the derivative at time 0 equal to 0. The basic steps are still the same. First, find the homogeneous solution, and this time we are going to do it a little faster, and you will get used to it after practicing. So set this equation equal to 0, assume a solution y equal e to the st, and plug in. Then we will find the characteristic equation being 3s plus 2 equals 0, and s will be minus 2 over 3. You can see that we can get this characteristic equation easily from plug in here, 3s plus 2 equals 0. That's a fast way to do it. The homogeneous solution is a equal a e to the minus 2t over 3. The second step, find a particular solution. So for the last problem, we assume a solution to be a constant because we had a constant here. But in this case, we will assume the particular solution to be ypt equals c e to the minus t because this is the form of the particular solution. And the yp prime is minus c e to the minus t, the derivative of yp. Plug in the original equation, we will get minus 3c e to the minus t plus 2c e to the minus t equal e to the minus t. You just plug yp prime yp, and this is still the same. Then we can see that these are the same. That's why we get c equal minus 1. Then our particular solution is ypt equal minus e to the minus t. Third step, form the complete solution. It is yt equal a e to the minus 2t over 3 from here minus e to the minus t from here. And we will go ahead and find the derivative of this equation because we will need it to find a. So take the derivative, we get minus 2 over 3a e to the minus 2t over 3 stay the same, plus, because the negative 1 goes here, e to the minus t. Okay. Last step, we will apply the initial condition to phi a. So the initial condition we have was the derivative at time 0 equal to 0. We will plug 0 into this equation. We'll get minus 2 over 3a plus 1. E to the minus 0 is 1. So this equal to 0, and we found a to be 3 over 2. And we put it all together to find the final solution. Yt equal 3 over 2 e to the minus 2t over 3 minus e to the minus 2t. So as we can see that the basic step for solving the first order linear and constant coefficient differential equation are the same for all the problem that we would see in 214. And the only difference is I think the guessing or assuming the particular solution. So we can see that the first case we assume a constant. In this case we assume a e to the minus t. So if we have a polynomial, we will assume a solution as a polynomial. Or if we have a cosine and sine, we will assume at a cosine or sine. So that's pretty much all to solve the first order differential equation.
Okay, so apologies for the slight glare, but we're just going to go in and start by solving a very basic second order differential equation. So as you can see here, this equals 0, which ends up making the particular solution 0 out. So the format you're generally given these questions is like this, but it also equals this same equation right here. And the same applies to the initial conditions. So the first step is finding the homogeneous equation. So you take all of these and you find their designated s's and s squareds and such, as Wynn probably described in the earlier video. And then you end up solving this equation to find your exponential powers. So in this case, when I plugged it into the calculator, you could do it by hand, you end up getting s equals -3 and s equals -1. So then you plug this into the general format of the equation to get -3t and -t right here, and this is your homogeneous solution. So moving on, the next step is finding the particular solution. So in this case, the particular solution is really easy to find because it is, in fact, going to end up being 0. But in the normal case where you had a constant on this side, say 1, 2, 3, 4, whatever number you want, you would say yp of t equals c, and then yp prime of t equals 0 because the derivative of a constant is 0, and then the derivative of 0 is obviously still 0. So then you would plug these back into this equation. So in this case, this is y double prime, so 0, there's no constant here, plus 4 times 0, which is 0, plus 3 times c equals 0. That's coming from this equation. So obviously 3c equals 0 amounts to c equals 0. And since yp of t is c, yp of t equals 0, if that distinction is clear. So the next step is you want to combine your particular solution and your homogeneous solution. Okay, so your homogeneous solution right here and your particular solution right here, you just want to add them up, and you end up with y of t equals c1 e to the -3t plus c2 e to the -t. And this is your general solution. Now, if you want your unique solution based off of these initial conditions, you're going to have to plug those in. So going on, we plug in the initial conditions until we can get our final solution. So we plug in the initial condition, y of 0 equals 2. And so t is 0 in this case, so we sub out these t's for 0. E to the 0 is 1, so these go to 1, both of them. So you end up with 2 equals c1 plus c2. Now, you have two variables in one equation, which is not enough, hence the second initial condition. So you find y prime of t, so you take this equation, you find the derivative of it, because the next initial condition is the derivative. So you find the derivative, and then you plug into this. So y prime of 0 equals -1, like the initial condition said. You put 0 here for t, and these also become 1 like they did above. So you end up with -1 equals -3c1 minus c2. Now, generally, you'll want to plug these into the calculator because they'll be much more difficult to solve. But in this case, you could have definitely done it by hand. And in that case, you end up with c1 equals -1/2 and c2 equals 5/2. So plugging this back into the general solution right here, you just get y of t equals -1/2 e to the -3t plus 5/2 e to the -t. And this is your final answer. All right, so we're going to jump to a problem that has a more difficult particular solution. As I said before in the previous problem, if the number was not 0 and it was a constant, it would be very similar to the way we had solved it, but you would have ended up with some constant particular solution. So starting with this problem, no coefficient here, coefficient of 2 here, coefficient of 1 here, and our particular solution will have something to do with this cosine. And these two are initial conditions, one for the non-derivative and one for the derivative. So starting like we always do, we're going to find the homogeneous solution. In accordance, like we did before, we find the s's. So in this case, it's going to be s squared here plus 2s plus 1. And then you solve for the s. So again, like I said, you could do this in the calculator, you can solve it by hand. In this case, it's easy to solve by hand. So this has a multiplicity of 2. As you know, for those who are in differential equations or who have taken it, the solution to that is to multiply by t, because you cannot just say c1 e to the -t plus c2 e to the -t. Otherwise, the math will tell you you're wrong later on. So just to avoid that, multiply it by t. All right, and then we're going to find the particular solution. So this is a bit of a longer particular solution than the previous problem. So starting off, if you guys remember from differential equations for cosine and sine, this is the general form of cosine or sine. And if there were to be both, this would still be the general form. So this is something that you would just want to put on your cheat sheet for your exams. You don't really have to memorize these. There's many of them if you do recall. This is just one of the many. So taking the derivative of that and taking the derivative of that derivative, you end up with these three. Plugging them back into this main equation and leaving the cosine, it is very crucial that you do not turn this into a 0. This cosine is supposed to stay and you're supposed to solve that way. Sorry, the camera keeps unfocusing. So you plug those back into the above equation, and solving that out, conveniently enough, this happens rarely, but conveniently enough, each of these equations gives you designated C2 and C1. Sometimes you might have to solve a system. It really just depends on how these coefficients end up canceling out. But I just grouped the cosines, including this cosine. This came over to this side, became negative cosine t, hence the -1 here. And two of these cosines, C1 and negative C1, canceled. So this is what you end up with for your particular solution, because in the form up here it says C1 cosine t plus C2 sine t, and C1 zeroes out. So this will be gone, and this stays as 1/2 sine t. So the next step is to combine these and solve for your initial conditions. Or not solve for your initial conditions, but solve using your initial conditions. So now we have the general solution right here by combining the particular solution and the homogeneous solution as stated here. From above, you know that the initial conditions are these: y of 0 equals 2, y prime of 0 equals -2. So you go in here, y of 0 equals 2 is obviously easier to solve for because we already have y of t. And you solve for, in this case, you will be able to solve for C1 because C2 zeroes out. When you plug in t, this goes to 1. This goes to 0 because t is 0. C2 times 0 times anything is going to be 0. And then 1/2 sine of 0 is going to be 0 as well, because sine of 0 is 0. So you are able to quickly solve for C1 in this case because this goes to 1, this goes to 0, so C1 equals 2. Okay? Then you find y prime of t. You just take the derivative of this equation, like y'all know how to do, and you plug in the initial condition down here. So in this case, neither of them zero out, but that's okay because we already have our C1 from up here. So we plug in our C1 and we solve for our C2, which ends up being negative 1/2. Now taking our C2, negative 1/2, and taking our C1 from here, 2, we are able to plug that back into this general solution to get the unique solution. So this is what the unique solution ends up being, 2e to the negative t minus 1/2 te to the negative t plus 1/2 sine of t. Now it's very important to note here, this C1 and C2 are not the same as this C1 and C2. I just use C1 and C2 very consistently, so I have just done that out of habit. So do not confuse these two with these two because they are not the same values. Clearly you are solving for C2, C1 here, and you already have those values, so you wouldn't be solving for them again if they were the same. So just keep that in mind when looking over this. And that's all for the bigger problem.